Okay, so on Wednesday, I introduced the one exercise is associated with the laminar flow, but in a channel. Okay, and I based on this exercise, we prove the relationship between the mean velocity and the maximum velocity. The ratio is 3/2. Okay, so the next one, we have different conditions, is also laminar flow, but in the round pipe. So please prove the relationship between the mean velocity and the V maxima. As we already know, the answer showing here is the ratio is 0.5. So the idea is the same. So we start from the definitions of the discharge. As we know, the discharge Q will equal to the integration with the velocity V. And then right now we know that the velocity function is dependent on the radius r. So there is the VR, and multiply the cross-section area. And in that case, we assume the flow directions is parallel to the cross-section area of the normal factor. Okay, so we don't use the dot product in here. We directly multiply two parameters together and do the integration. And we know that how is the small piece of the dA. As you can see showing here, as I mentioned, the cross-section area for the small piece is the ring shape. So the ring shape, the area is equal to 2 pi r and the dr. So we can rewrite the integration to be the I just put the function in here. So 1 minus the r squared divided the capital R squared. The capital R is the total radius length of the pipe. Okay, and the V maxima and the dA is equal to the 2 pi r dr. Because this is the integration problem, so we need to know the interval for the integration operator. So the interval is start from the 0 point in here to the total radius capital R. Okay, so we can summarize, reorganize the equations. We just take outside for the constant value, that the V maxima and the 2 pi is the constant. So inside I only have the 0 to R, and I put the R inside combined with the velocity functions. So here is R minus R cubed divided the R squared. Okay, and still have 1 dr in here. So right now we only have the functions related to the R, and we do the integration. So there is a 2 pi V maxima, and we do the integration will be equal to the 2 over R squared, and the minus the 4 times R squared over R 4 power. Okay, and the interval is start from 0 to capital R, the total radius. Okay, so we just put the number inside. So there is a 2 pi V maxima, and we put the radius inside. And we don't have a 0, right? You put the 0 inside, there is no result. So we only have the capital R. The capital R is 2 over R squared, and the minus the 4 times R squared over R 4 power. Okay, so you can do the summarize. The final result will equal to the 4 and 4 over r squared, right? The 4 over r squared. Because here you can cancel out the square, and there will be 2 the r squared. So you just balance the equation. You know, finally we only have the 4 over r squared. Okay, so that will equal to the 2 over v maxima and the pi r squared. Okay, but go back to see our purpose. The purpose is we would like to find out the relationship between the mean velocity and the v maxima. So until now, we don't have the mean velocity in our equations. So we know that based on the equation, we know the q will equal to the mean velocity multiply the total area. Okay, and we know that the total area in our case is the circle shape with the radius r. So the total cross-section area is pi multiplied the r squared. Okay, so we know based on the equation showing here, we know that the mean velocity is equal to the discharge divided the total area. And the discharge already showing here the result, and you can divide the total area is equal to the pi r squared. Okay, so finally you know that the answers for the mean velocity is 2 over v maxima. Okay, so we prove the relationship between the mean velocity and the v maxima is only have the 0.5 factors. Okay, so in the later exercise, I will let you know how advantage if we know the mean velocity before and for our questions. Okay, so you can keep in mind 2 important relationships. For the round pipe is the 0.5. But for the channel flow, this is 3 over 2, the difference. Okay, so based on different conditions, you can have a different relationship between mean velocity and the v maxima. Only 2 different conditions, the channel flow and the round pipe flow. Okay, so that's the table just summarize how can you compute the discharge by yourself. So totally, we only have the 3 cases. The first case, if you know the mean velocity, this is case 1. You already know the mean velocity and you know the total cross-section area, so you can compute the discharge very quickly if you know the mean velocity before. Okay, and the second, if not, you don't know, and you know the velocity in here is non-uniform. So the velocity in here is non-uniform flow. So because it's a non-uniform, so we need to use the integration to find out the discharge result. Okay, but in that case, we assume the flow velocity always, the directions is always parallel to the normal factor of the cross-section area. So based on this equation showing here, you cannot see the dot per dot. But the final journal formula in here, we have the velocity function dot per dot with the cross-section area. So it's different because in here, we didn't know the velocity flow direction is parallel to the normal factor of the cross-section area. We don't know. So we need to use the dot per dot operator in here. So that's only the case 1, and this is the case 2, and this is the case 3. You should, based on your questions and looking for which one is the better for your questions. Okay, and if you compare, so the upper is related to the discharge, and the bottom in here we show the end rate. The end rate is the mass flow rate. The only one difference compared to discharge is we have the additional density in here. We have the additional density in here because the density multiplied by the discharge will equal to the mass flow. Okay, so that's a table summarize all of the information we have learned before. So in the following, we have 3 exercises, and based on our exercise conditions, you can choose which one is the better for your questions. Okay, so the first one, we already know the density, and the density in here for the air. So the material is the air. So you have the air in here, and the density is the 1.24 kilogram per meter cubic flow in the pipe. So in our questions is the media is the pipe. Okay, so this is the pipe flow, and we have the diameter is 30 centimeters. So it's equal to 0.3 meters. And we actually know the mass flow rate. The mass flow rate, so mass flow rate, the end rate, is equal to the 3 kilograms per second. So what's the question in here? We have what's the mean velocity in this question, and what's the discharge in the pipe. Okay, so and the question require we use the system unit to answer the question. So, but in class we only focus on the English unit in here. Okay, so what do we have? We only have the 3 conditions, and we can start from the end rate, because we know that the end rate will equal to the low density multiply the Q, right? But right now we need to answer how large it is of the discharge. The discharge, we don't know. So we know that the Q will equal to the end rate divided the density. And we know that the end rate is 3 kilograms per second, and divided the density is 1.24 and a kilogram meter cubic. Okay, over 1. So you can calculate the distance very quickly. So you have the 3 divided 1.24. Okay, that will equal to around 2.42 meter cubic per second. So very quickly, we know that this is our first answers, right? But you just pick out which formula you need to use to answer the questions. The second, what is the mean velocity? So we know that the Q discharge will equal to, if we know the mean velocity already, and then multiply the total cross-section area, right? So we know that the mean velocity will equal to the discharge divided the total area. So in here, we can compute the total area first. So because this is a round pipe, so the total area is equal to 2 over pi d squared. So we know that the diameter in our case is equal to 0.3 the square. So you can compute the total cross-section area by yourself. So I use my calculator to compute the total cross-section area is 0.07065 meters square. Okay, so we can directly compute the mean velocity is equal to discharge is 2.4 0.042 meter cubic per second divided the total area is 0.07065 meter square, and you can calculate the final result. So I use my calculator to double check the answer. So that will equal to the 34.2 around the meter per second. Okay, so very simple exercise. You just take a look and which parameter you already have, and then you would like to answer the questions is related to the mean velocity and the discharge. So you just pick up the equation you need to answer the questions. So that's the exercise 1. And then in the following exercise, you see I highlight for this question we need to use the dot product. Why? As you can see, we have known the flow direction is along these directions, okay? But you double check the cross-section area. It's not normal to it's not the normal factor of the cross-section area is not directly parallel to the flow directions. So the first one, your true cross-section area is along these directions. So it's not the parallel. So you need to use the dot product to compute the answers. So the inside is the water flow in the channels has the slope is 30 degrees. And if the velocity assumed to be a constant, that means this is the uniform flow, right? The uniform flow. So the uniform flow, we don't need to use the integration because the velocity is the uniform flow. So always the constant. So we know that our first condition is the uniform flow. So the velocity is always the constant value. And if the depth, the water depth is the 0.6 meter. This is the water depth. Okay, and already tell you the measure along the vertical line in here. And what's the discharge? What is the discharge? And the per meter of the width of the channel. So the difference in this question, we didn't know the channel width, right? We cannot catch the answer related to the channel width. So we assume the channel width is W. We don't know the width of the channel. Okay, so it's a W. So go back to our questions. We know that the Q should be equal to the velocity factor, right? The velocity factor dot with the total cross-section area. Okay? And we know that that will equal to the V factor absolute multiply the total cross-section area absolute factors. And because this is a dot product, so we need to cosine theta, right? And then we actually know the intersection angle between the velocity and the cross-section area is the 30 degrees. Okay, so we know that this is the 30 degree cosine. And then we just look at the answers. So the velocity we have known in here is 12 meters square. So we have 12 meter square. And what's the cross-section area? The cross-section area in here, we know that the water depth is the 0.6. It's the water depth. And we don't know the channel width. So here I use the W. We don't know the channel width. So the water depth multiply the channel width is the cross-section area. Okay? But this cross-section area normal factor is not parallel to the flow directions. So we need to multiply the cosine 30 degree, right? We do the dot product. So we just balance all of the numbers showing here. So the 12 multiply 0.6 water depth, multiply the cosine 30 degree. So that will equal to around the 6.235, and the additional unknown operator in here is the W, is the channel width. So we have additional W, and the units in here is a cubic meter per second. This is a discharge. Okay? And then because the question require we answer what is the discharge per meter of the width, per meter of the width. So we assume in here, we assume the W is equal to 1 meter. And then we can compute the small q is the discharge per unit meters of the width. It's a q divided the w, and right now the w width is equal to 1 meter. So we can tell you the answer is 6.235 meter square divided the second. And usually we call that is the flux. The Chinese we call that the 通量. Okay, 单宽通量. Okay, that indicates the unit will change to the meter square per second, not the cubic meter per second. The cubic meter per second is discharge. Okay, it is a very useful parameter when we discuss the hydraulic problems. So you can see the difference. We use the small q. Okay, so the second exercise we practice already is the idea is the flow directions is not parallel to the normal factor of the cross-section area. You need to use the dot product. But for second exercise, we still assume the flow is a uniform flow. So we don't need to use the integration operator for our questions. So you can know that the third exercise in here, I highlight what we need to use is the integrations. So right now we need to use the integrations. So again, we have the velocity functions. And this is the velocity function, what we have the showing here, right? The velocity function already showing here. So we write down the velocity, and this is the velocity profile is as a function of the y. That indicates the different y directions, the point we have the different velocity. Will equal to the u maxima and the y divided the d and the root. Okay, so this is the exercise we are very familiar because this is we call that the quarter flow, right? This is the standard quarter flow in here. And what's the problems? And the inside is the water. So this is fluid media is the water. And what's the problem? We need to answer what's the discharge in the channel flow. If the water in here, the depth is equal to 2 meters. So we have the water depth. The D is the water depth. And for this question, we already know the width of the channel is 5 meters. The width of the channel is 5 meters. Okay? So the maximum velocity in here is 3 meters per second. So we have a maximum velocity is 3 meters per second. This is the maximum velocity. Okay, so that's totally we have the 4 conditions for these problems. Okay, because the velocity function is not uniform flow. So right now, if we need to answer the discharge, how large it is, we need to go back to see our government equation here. Well, 2 equal to the we have the velocity function, right? We have the velocity functions, and we need to dA, right? dA. But how about the dA? dA we can change to the I just write down the U velocity is equal to the U maxima and Y divided the D and the root. And what's the dA? dA, the small cross-section area is the width. Is the width multiply the small y change. A little bit y change, but multiply the width of the channel is the cross-section area, dA. Okay, and then we know that the integrations will start from the bottom of the channel to the top. So the integration along the y directions will start from the 0 to the D, the total water depth, right? The total water depth. So I just put all of the constant value outside the equation integrations. So the U maxima is the constant, and the width is also constant. And we do the integration 0 to D, and the inside we only have the Y, D, and the 2/1 and the dy, right? So we need to directly to find out the integration result. So the U maxima multiply the width, and then we do the integration inside will equal to the first one we have the YD, and the power is the 2/3, right? And so we need to have the additional constant is 3/2, and we have additional D outside, because after we do the differential and we have additional D/1 constant value. Okay, and the interval will start from the 0 and to the D. Okay, 0 to D. Okay, so you can summarize there will U maxima and the width, and there will we put the Y is the D, right? So we put the D inside the equations. So D divided D is equal to 1. And 1 for any powers in here, 1 for any powers is also the 1. So finally we only have the 3/2D, okay? 3/2D. Okay, so that's the you can put all of the number inside. We know that the U maxima is the 3 meter per second, and the width is the 5 meters, and there is a 3/2, and the D, the water depth, is the 2 meter. So you can compute the final answer is equal to the 20 meter cubic per second, right? Okay, so this is a final answer what we have based on the integration formulas. But one thing in here I would like to emphasize, as I mentioned before, if we already know the U maxima, how can we compute the discharge? We can only based on, so this is the method 1. And another method in here, we know that the Q will equal to the mean velocity divided the total area, right? The mean velocity divided the total area. And since the exercise already tells us the maximum velocity is 3 meters per second, So we know that the relationship, the baseline relationship for the channel flow, the mean velocity will equal to 3 over 2 and the U maxima, right? That's based on the channel flow ideas. So we can, and we know that the total cross-section area will equal to the water width divided the channel width multiply the water depth. So that will equal to the width is the 5 and the water depth is the 2. So this is equal to a 10 meters square, right? And the U maxima in here is the 3 meter per second. So we know that the U mean is the 2 meter per second. And you already know the mean and the total area, so you can quickly compute the discharge is equal to 20 cubic per second. Okay, so only 3 very simple equations, but we can find out the discharge very quickly. We don't need to deal with the integrations. We just multiply some constant values and then we have the same answers. Okay, so that's an idea very important. That most important thing in here is if we already know the mean velocity, anything can do very quickly. Okay, if you didn't know before, so you need to use the integration to calculate the answers. 那这个我觉得很重要是，如果今天考试时间只有5分钟，那我出了10题。那如果你知道这种关系式，那你用蓝色这样的方式，不是一下就算完了吗？可是如果你去做积分，很容易做错，但是你又比较花时间。那所以有观念比较重要，不一定什么东西都要把它算出来，很快的把它算出来。你如果有观念，其实你一下就算好了，我觉得这个是比较重要的观念。可是积分也没有错，因为那是最本来的暴力破解法。你最本来的方式，你也可以用积分去做。Okay, so that I share you 3 exercises and based on a different formula to find out the same discharge. Okay, so that we need to move to the ninth slide. The topic is associated with the tool. As I mentioned, we have a two approach to understand the physical property exchange along the boundary. Okay, two approach to understand the physical property exchange along the boundary. Okay, and so we have two ideas. The first one is we need to know what is the control volume. What is the control volume? And the second, we need to know what is we call that the closed system. Closed system. So the figure showing here, I highlight and depict the closed system boundary. So this is our closed system boundary depicted by the yellow line. And then the right hand side of the sentence, as I mentioned, some very important idea. Because the system, we call that the closed systems. So any physical property cannot cross along the boundary. Okay, any physical properties cannot cross along the boundary, such as the mass cannot exchange along the boundary. That's why we call that the closed systems, right? And then we have a piston and moving downward, so you can have a compression force. And then after the piston downward, the closed system will deform, right? And then maybe move to the bottom. So that's the second idea. The closed system boundary can move and deform. The closed system boundary can move and deform. But no any physical property can exchange along the boundary. So we call that the closed system. And usually the closed systems is the Lagrange concept. I think all of you already forgot what is the Lagrange. But the Lagrange is just the idea we have the closed systems, and I pick out the one fluid particle. I pick out one fluid particle, and I observe this fluid particle moving at a different time point, and see what happened, what the particle, where the particle locations. I just observe and track only one particle. So this is, you can do that only for the system is the closed system. Because the closed system, all of the fluid particle bound inside. So you can observe where is the particle. If not the closed system, it is very difficult to observe the particle moving. Okay, and so we call that is the Lagrange concept. So what is control volume? So this is the idea. I depicted the control volume boundary. So the dashed line, the yellow line in here is our control volume, the control volume boundary. And we call that is the control surface. Control surface. The boundary, the dashed line in here is the control surface. And so inside, we call that the control volume. So it's a CV. CV is the control volumes. So how different compare the control volume with the closed systems? You can see we have some input. We have some input, right? And then we have some output. So that means for the control volume, the physical property can exchange along the boundary. We can have some inflow, right? And the layer is the outflow. So that means the boundary of the control volume, the property can exchange along the boundary because we have the inflow and the outflow along the boundary. Okay, so the significant difference compare the closed system and the control volumes. Most important thing is you just determine the boundary can exchange the physical property or not. If cannot, we call that the closed systems. If it can, so you can say that's the control volume. So the control volume is based on the Euler's concept, because the Euler concept is related to the spatial location. The spatial location. So you just looking for your problem fixed on some locations. So we call that is the Euler concept. OK， 所以封闭系统跟控制容积只有一个非常大的差异是边界是可不可以交换。那我们都知道封闭系统当然边界就不能交换，要不然怎么会叫封闭系统？那控制容积就是边界是可以交换的。那第二个是他们的想法不一样。封闭系统我们会用 Lagrange 的想法去做，因为 Lagrange 就是会追一个台风，然后我就追着台风跑去哪里了。那尤拉的想法是说，我只看这个空间，这个空间有什么变化，我只在这边看，你以外的东西我都不在意。所以尤拉就是有点像空间函数，那 Lagrange 有点像时间函数。我先跟你讲，他现在在这，那1点以后他跑去哪里了？我就一直在追这个东西。那讲白话一点，就是 Lagrange 有点像 initial 的 condition， 就是你要先给我起始值，我才知道未来怎么走。那尤拉法就是你给我 boundary condition， 那我就一直都在这里。OK， 这是两个重点。OK，so 来这the tree structure just highlight if you looking for one problem, how can you distinguish or decided which system you need? You need to consider the closed system or not. If you just consider control volume approach, how can you see the difference? So you see the the larger difference in the different concept, the Urian and the Lagrange, and related to the closed system and the control volume. And for the closed systems, you only see some particle, the particle only, right? Because we need to fix the particle and to check the particle and to see the particle, what happens at the different time period. But for the control volume, we don't know. We don't need to fix the particle. We just fix the regions in space where you are looking for. Okay? And then the closed system is quite very useful to isolated systems. Because the isolated system, the energy cannot dissipation. So that's the closed systems. Okay? And then, so that's the tree structure just summarize how different they are. So I already emphasized. And the table just put some important sentence, the Lagrange approach and the Urian approach, control volume and the closed systems. That's all. So, and then you can see the mass is allowed to close the boundary. It's for the control volume. But the closed system cannot close. Okay, that's some very important idea. Help you to distinguish two approach. Okay, so most of the problem we use in this class, we use the control volume because we always looking for one spatial locations, the spatial locations. Okay, so after we introduce the two approach, so that I always mention the physical property and the physical property. I always emphasize the physical property. So how can we distinguish the different physical property based on some ideas? So in this chapter, we have two courses, the intensive and the extensive. The intensive and the extensive. So how different they are? You can see the intensive. How can we call that the intensive properties? You see that indicates the properties are independent on the amount of the matter present. So what's the meanings? We can go back to see what is the intensive properties, such as the pressure, temperature, and the density are intensive property. So if you go back to see what is the density, the density divided by the mass divided the volume, right? And we say that is the independent. What are the meanings? Because you can see if the mass increase, the density will increase, also decrease. If the mass increase, how change in density? As we know, the density didn't change, right? Because the small matter, the same matter, but the small one or bigger one, they are the same density, right? So that means independence on the amount of the matter. Matter 通常 matter 就是本质嘛，那本质就是质量，就是我的本质。其实我不会跟质量有关系，就算质量增加了，我的密度也不会变。那这种参数我们就叫做 intensive. Okay, so as we can see, in other words, the extensive property will depend on the amount of the matter present. As you can see, the mass and what is the momentum? The momentum will equal to the mv, right? And what's the energy? It's equal to 2 over 1 mv squared, right? And what is the weight? The weight is the mg, right? So all parameters, properties showing here, they are as function of the mass. because the mass increase, the momentum will increase. And the mass increase, the energy will increase. And the mass increase, the weight will increase. So I tell you the extensive properties are depends on the amount of the matter present. So the most important, you need to distinguish what is the intensive, what is the extensive. You just based on the dependent or independent. Okay, the dependent or independence. And then the final sentence I tell you, many intensive properties are obtained by taking the ratio of the two extensive properties. So sometimes you can divide the two extensive property to create the intensive. Okay, so maybe we can stop here and 10 minutes break. And the next class we will introduce based on the intensive and the extensive properties, and we will introduce what is the property transport. How can we define the property transport in our problems? Okay, so we have the 10 minutes break, and then we just go back the class after 10 minutes.